hello everyone. Today I will do my best to tell you about long-term solar activity. This seminar is supposed to be informative, so if you have any questions during the seminar, you can stop me and ask. Don't hesitate. So, okay. Well, but I think it will go to well. If it goes to the 10th one, don't panic. Okay, so let's start in this title. There were two things: long-term and solar activity. Let's start with solar activity. This is examples of how many different indices there are that give us information about solar activity. There is the radio flux that Antonio mentioned. This is one of the most well-known indices because it started being observed in 1947. We call it S10.7. That's something very... And there are different radio fluxes. That's why I say it at the plural. There is not only the F10.7, but it's the best well-known because it was the one that was observed first. There is the flare index, and this is really interesting because it started... Well, in fact, the sun flares. You might have heard about that. And there are some flares, interestingly, observed in white light, but it's most interesting to observe it in H-alpha. And George Hilary Hale from the Mount Wilson Observatory started developing an observing technique at the beginning of the 20th century. But the actual H-alpha patrol, so consistent observations of these flares, started in 1938. But you can still find a few observations before that. There is, of course, the X-ray flux observed by many satellites, like the GOES. There is, we can find information on solar activity in the magnetism from Earth, geomagnetism. There are many indices also there because it started being observed a long time ago. There is what we call the magnetic needle that was observed in the 1780s. There is the AA index that started being observed in 1868. There is a DST, the AP index, the KP index. There are many indices for that because, of course, we could observe them more easily from Earth than anything from the sun. There is the solar magnetic field itself, and there are information from cosmic rays. Well, the cosmic rays that arrive on Earth are modulated by the magnetic field, so it also can give us information on the sun. There is coronal index. There is the solar irradiance, total or spectral. There are different flux, the UV flux, magnesium 2, calcium K, and there is the sunspot area, the area of those sunspots that Frédéric told us about in the last two seminars. And there is, of course, the sunspot number that we started observing in 1610. And when I say we, I don't mean we here at SILSO, for example, but Galileo, for example, started observing them in the 17th century. Now, what is the sunspot number? So this is what it looks like. It's a quantity that counts you've seen it already in the first few seminars. It counts the number of spots and groups of spots on the sun every day through a worldwide network. And it's really interesting because, of course, it goes back 400 years. And we're going to develop specificities in more details later, and especially we have to keep in mind that it was recalibrated recently, as Antonio mentioned. And so sometimes there are figures that present the old sunspot number and that haven't been updated. And so what do the other indices that I mentioned look like? There is this radio flux, and you see the figure on above starts actually at the beginning of the series. It looks a lot like the sunspot number. Well, it looks a lot like the sunspot number. You can actually see this pretty nice cycle that you can see on the sunspot number in this index too. And I added the figure below because actually the previous one doesn't show cycle 24. And there was an interesting things happening between the flux at 10.7 centimeter and the sunspot number, because at some point there is a relation that can be established between the two, but it might not be always valid for all the time, of course, as it started in 1947. The sun might change regime between 1947 and now, and so relation valid in the 1950s might not be valid today. So it has to be checked. There is here an example of the AA index. You can also see the influence of the solar cycle. So in black is the sunspot number and red the AA index. There is the influence of the solar cycle in this index. Of course, as it's geomagnetic, it can be influenced by other things than the solar activity. And here is a plethora of different indices. You can see the sunspot number in the panel above, but you also have the cosmic rays I was mentioning. So as you can see, the number of cosmic rays arriving is inversely proportional to the actual solar activity. You have the X-rays from the sun that you measure with gauss, protons. As you can see, it's not so easy to find the solar cycle, but you can actually see that there are more when the activity is higher. And it's the same for the magnetometer, but it's not. Again, there is another modulation here, but you can still see the solar cycle. So we can separate these indices in two main categories, like the direct measurements and the indirect measurements. So the direct measurements are the ones that we can make at the sun or from the sun directly, like the TSI, the SSI, the number of CMEs that come from the sun, the solar energetic particles, the sunspot number, the group number, the sunspot area are direct indices, although you could say that they are not physical quantities. Exactly, some will argue that the sunspot area is a physical quantity, while the sunspot number is not as physical as the sunspot area. There is the coronal index, the number of solar eruptions, the flare index, etc., etc. And there are the indirect measurements. There is the geomagnetic data that is taken at Earth, so can be influenced by other things. The number of Orioners, and one very interesting index, it's the data from the cosmogenic isotopes that can give us really good insight in the sunspot. So one typical interesting example of the indirect measurement is made through cosmogenic isotopes, as I said. There are cosmic rays that arrive from outside of the solar system to the Earth, and they in fact give us ideas about the open solar magnetic field. They are modulated by it, and they are stored in natural archives. So the varying solar magnetic shielding modulates the flux of these cosmic rays, and cosmogenic radionuclides natural, can provide information on this magnetic field in ice cores. So it's a deposition that is recorded in ice cores with beryllium-10 and in free rings. So it's the carbon cycle that is influenced, I think. The problem is in that case that it's very indirect. Not just indirect, it's the most indirect index. Because it can be influenced by many different processes at Earth and also in the galactic background. So for example, variations on a geological timescale can be due to the changing galactic background and not to the sun. There can be changes of influence of the geomagnetic shielding. There can be transport effects in the atmosphere that will impact the beryllium-10, or deposition effects and carbon cycle effects that can impact the carbon-14. So, and there are others like that. So this index is really interesting because it can go back 10,000 years. So it's very good if we want to know how the climate varied on Earth. But we have to understand all the different layers that go from those tree rings and ice cores back to reconstructing the solar activity, and it's a bit complicated. And it also doesn't give you a daily resolution. There is no way you can reach the daily resolution with something like that. So let's take a look at something like, it's not 10,000 years, here it's 2,000 years. It's a recent article by Laure that was published in the topical issue of Solar Physics concerning the recalibration, which means it actually takes into account the new sunspot number. And you can see here 3 reconstructions of the solar activity through those cosmogenic isotopes. The first one is beryllium-10 from Greenland. The second one is beryllium-10 from Antarctica, and the third one is carbon-14. And so we're from the top, sorry. So Greenland green, Antarctica blue, and carbon-14 in red. As you can see, the only differing thing here is the green one at the end seems to show a very high rise. This would be associated to what we used to call the grand maximum. But the other two ones don't show a grand maximum. So we'll come back to that later. Yes, yeah. I think it's a different station that is used. As you can see, the error bars on the carbon-14 seems to be much larger than on the beryllium-10. And so here you have those two stations, I think. You have MB and KU, so there. And so you can see here that KU goes to the end while MB doesn't. So on this figure, you have carbon-14 in orange and red. You have the old group number in dashed black. So Hoyt and Scatten 1998 is the old group number. And you have the new ones in blue and black above. And as you can see, the old one doesn't follow this carbon-14 reconstruction, although the new ones do. Now for the beryllium-10, you can see the Antarctica reconstruction in green. So it's inverted. This is not the Greenland reconstruction. The Greenland reconstruction is actually in red here. So the Greenland follows pretty nicely, in fact, the sunspot number, while the Greenland in red doesn't follow very well. Well, in red and orange. So, and this shows this. You see this upward trend at the end. You can also see it here in more detail. Now we have a very nice direct measurement of this solar activity, and it's of course I work on the sunspot number, so I will develop a lot on the sunspot number because it's in fact the most well-known and the longest direct measurement of solar activity anyway. So the number of structures on the sun has been counted since the time of Galileo, but here you don't see sunspots until the 1600s. And this is because actually it's the data are pretty reliable until the 18 something. Wolf started counting in 1850. Before that, he did a reconstruction of data for about 100 years. So it goes back to 1750, and there are a few data between 1700 and 1750, but the resolution is even worse than the rest. Well, you don't have an observation per day, certainly, so that is why you see that the black part is at less resolution than the blue part, for example, on this graph. So the full story is that if you want to go back to 1610, it's not actually the sunspot number or the number of the Wolf number that it's used to count. It's actually the group number. So the sunspot number is what you see on the left here, this formula here. We sometimes also call it the Wolf number. That's why I put a W in this formula. So it's in fact 10 times the number of groups plus the number of spots. This formula was invented by Rudolf Wolf in 1849. And if you wonder about this 10, I would say it's because at the time, the average number of spots per group was close to 10. But if you actually read texts by Wolf, he will tell you that I didn't want to put 9 because it's not so nice, and I didn't want to put 11, so I put 10. Well, because at the time, anyway, it was really close to that. But if you do the actual average number of spots per group today, it will not be 10. But it's a formula that is used to count the sunspot number even now. And the group number is based only on the number of groups. And so it's supposed to be less sensitive when you have a high number of spots and you don't exactly see the small ones. Okay. And the sunspot number was, in fact, reconstructed completely from the data in the 1990s. So it's a bit different. Sorry. So the full story is not all in the sunspot number. It's in the sunspot number and the group number. So why do we count sunspots? I think what are they is a very nice image of the spots, and you have had an answer in Frédéric's talks in the last few weeks. So those sunspots actually represent the magnetic activity of the sun. That's why we count them. And it's an index of solar activity. It follows the magnetic field, as you can see here, the butterfly diagram that you also saw in the in the presentation from Frédéric. I checked this morning. And so I refer you to those seminars for the actual of what is a sunspot. But what is interesting here is if you compare the sunspot number to other indices, what information do you have? I put all of that here, and the most interesting part of this slide is this figure from Thierry de Witte from 2012. It's actually a separation in 3 sources of different indices on the x-axis. So you have the radio fluxes, you have the alpha, MG2, daily sunspot area, the sunspot number, and the group number. And what you can see is actually they all say something similar. They are, of course, all related to the sun, and you will find the sunspot cycle in there, but they are all related to different physics of the sun. So they all tell you a bit of a different story about the sun. Now I'm coming back to this relation in more details about the F10.7 and the sunspot number. When we compare F10.7 to the sunspot number, there is a very nice relation between those two. The graph on the right is older data where you could see actually the departure in white is cycle 24. You could see actually a departure of F10.7 from the sunspot number. It's still there with the new sunspot number, but less visible, less obvious. And this in the upper right is the relation of the new sunspot number with the flux at 10.7, sorry. And as you can see, it's not a linear relation. So it depends on a minimum value. Here it's like the 68 that you can see in the formula, but it can go lower than that. And it's not absolutely linear, but there is a relation. As I said, be careful. It might not be, because it holds now doesn't mean it held in the past or it will hold in the future. So we have to be very careful about that. Now, TSI versus SSN. It's also an interesting story here because the TSI was observed from 1978 onwards through satellites, because it's not so easy to observe from the ground. And all of the satellites give us very interesting measurements of the TSI, very precise. But these satellites are really not easy to scale to each other. So the composite itself is very hard to make, and so there are scientists that will trust one composite and scientists that will trust another composite, and it's a story that is very similar to the one of the sunspot number, in fact, and although it's very modern. So what is interesting here is that the TSI is not only linked to the sunspots, but also to the faculae. So if you model the TSI, you have the darkening by the sunspot and the brightening by the faculae. If you go back in time, you don't have the faculae information. So in fact, you have to derive it from the sunspot itself. So it's even less accurate. And there is also a relation between TSI and the sunspot number. It's even less linear than the one between F10.7 and the sunspot. But it's also very important for what we do. TSI is especially important for the climate. I will come back to that a bit later. So now, if we want to understand this series and solar activity correctly, we have to go into the history. So I start with the prehistory, because actually before 1610 there were observations of the sun, but it's mostly naked eye observations through fog, things like that. So you can find information, but it's not really usable if you want something for climate studies, for example. If you go back to Galileo, you have drawings like the one here, or it's a plethora of different kinds of drawings. It's not always easy to interpret. So there are people like Rainer Alt in Potsdam who have created softwares to actually use very old, very non-homogeneous data to actually compute the area of the sunspots, the positions, and many, many different interesting things that we can use now. And so now we go to the history. So let's start here. In 1849, Wolf actually started observing consistently with the telescope you can see here. It's actually a refractor. And that's an image of Wolf. There is another image in the solar dome here, on which is much older and much more impressive. And he also did something very interesting, as I said. He reconstructed data, so with three main observers that you can see in red on the yellow square. So Schwabe, Flaugerg, and Stauder. I think Schwabe and Stauder are German, and Flaugerg is a French guy. And so those three main observers were the ones for which he had data back to 1749. So basically 100 years. And so it's really interesting, of course, but of course these guys didn't observe every day. So it's not the same as having a network. You will have gaps in the data. And after that, there were different directors of the Zurich Observatory where Wolf was working. There was a guy with a name very similar, Wolfer, that observed after Wolf, and in fact he observed also at the same time as Wolf for a few years. There is after that Brunner, and after that there is Max WALDMEIER, that was still the director of the Center for Observations until 1980, and in 1981 the center was transferred to SILSO. What is interesting in that sense is that in 1957 Zurich opened a second base station because the weather was not good in Zurich, or they decided it was important, in Locarno, so almost in Italy, and they hired a new guy that you can see. So Max WALDMEIER is actually on the right in the picture on the complete right, and on the left you can see Sergio Cortesi, who is still observing at the Locarno station today. And when we transitioned from Zurich to Brussels in 1981, we used this station as a transition station because actually it was the only station that was common to before and after. And so it's really important to know this Locarno station. Okay. Now we will come to SILSO itself and the present a bit later. The group number, as I explained a bit earlier, was created by two US scientists in 1996. And what they did is actually they took all of the existing data on observations back to 1610 and used this data to compute this group number. They didn't use the sunspot number. They used the original data. And it doesn't have the same sensitivity to IR regime because you don't have this problem with the limit between what is a spot and what is not a spot when there are lots of spots on the sun. But the thing is that it could be more sensitive to the group splitting. When there are a lot of groups of spots on the sun, it's not always easy to distinguish between two groups. And here is the group number. On the upper panel, you can see the original group number and the recalibrated group number in blue. And below is the ratio between the original and the recalibrated. And as you can see, you don't have the lines here, but the original group number in red did show what we used to call a grand maximum, meaning that in the most recent period, it seemed that the level was much higher, but on the blue thing, you don't see a grand maximum anymore. It seems the cycles from the 18th century are the same level as the cycles from now. Now, last year there was an issue of solar physics, a topical issue of solar physics that went out because those two series, sunspot number and group number, have been under severe scrutiny, and there is an ongoing effort of recalibration, and we have to take a look at that to understand what happened. So here is the same curve, but here I show you what was corrected, what was done to this series. So in fact, it was actually also reconstructed from the data with new interpretation of the data, because in the Huygens-Scatten group number, in fact, there were some problems in the way they counted groups. They interpreted some archives not in the right way. And so there is a new reconstruction by Salgardin and Scatten, the same guy. And so there was a correction of the Greenwich trend. So there is a well-known catalog that is called the Royal Greenwich Observatory that has data on the sunspot from 1874 to 1976, and after that the catalog is filled in with values from Boulder, from the solar region summaries. And at the beginning of this catalog, there were some problems mainly we would call that a learning curve or something like that, but it's not completely stable between 1885 and 1950. And so it has to be taken into account because the main source of the group number, why is it moving itself? The main source of the group number at that period is the Greenwich catalog. And so what is very interesting also here is the MAUNDER minimum. It was revised by a Spanish team of scientists, and they have led by José Vaquero, and I will show you a bit later. But before that, we had the idea that there were no spots during the MAUNDER minimum, and in fact there were a few, but they are not easy to find in archives because people lost faith in the sun at that time, and sometimes they didn't write correctly or they stopped observing, and so it's not as easy to find. Now we go to an overview of the sunspot number corrections, and the sunspot number here shows 3 main corrections. And those 3 were applied. There are other corrections that are in the process of being reviewed. So the first correction that was applied is a temporary shift that you can see in the Schwabe-Wolf transition. It's for a few years. There was a jump in the scale. After that, there is a jump in 1947, that is due in fact to the director of the Zurich Observatory, Max WALDMEIER, that I told you about earlier. And so this guy decided in 1947 that we were going to wait the counting of spots. And after that, we used the Locarno station as a pilot station because it was the only common station between for the transition. And this station had a drift. And what you see on the ratio is in fact the drift that has been corrected. So I summarize here what has been corrected in the sunspot number. So we have removed the 0.6 scale that was there before. So mostly the SILSO number was always lower than the other sunspot numbers because we used the Wolfer correction, meaning that to follow Wolf scale from before, Wolfer decided that his numbers would be multiplied by 0.6, and we continued that thing forever until 2015. And so after that, there is the Zurich-Brussels transition, the WALDMEIER transition in 1947. There is a correction under review for Wolf-Wolfer. The Schwabe-Wolf transition has been applied, and the Stauderer-Schwabe transition is also under review. It hasn't been applied to the version 2.0 that is on the website at this moment. So interestingly, I will just go into a few details on the Zurich-Locarno transition. It was diagnosed by looking at the average of the network. We can do that actually because now at the SILSO network we have a worldwide network. So we have many stations giving us information at the same time. So you can actually look at what the other stations say, and we have all of this data in a database. So we can look at it and say, it's really strange because actually all the stations say the same thing except for the Locarno station. And that kind of diagnostic would not have been possible at the time of Wolf, because actually it was data was used as one single observer. So even if there were like 2 or 3 people looking at the sun, there was the director that said, I will take this one for today. And most of them are recorded, and we are now in the process of digitizing this information, but it's not fast. It takes some time, but we will have that kind of information from on the past when we are finished with that kind of digitization. Now for the WALDMEIER transition, what is really interesting is that the director Max WALDMEIER from 1944 to 1980, I think, decided in 1947 that we were going to introduce a weighting on counting the spots, meaning that if a spot was big, the definition is not so clear, we were going to count it as 2 or 3 and not just 1. And if the spot was really small, it could be counted as 1 or even less than 1. And so, of course, it changes the scale of the counting. So the idea here was to try and define this jump because we knew there was a problem at this point. We had to pinpoint the exact date, and we had to pinpoint the scale of the problem. And so there were studies by Lockwood et al. In 2014 that tried to compare the sunspot number to different solar indices, solar activity indices, and tried to find how to quantify this difference. When I redid this analysis, I found something like a 16%, 17% jump. Now, what we did was also to do that by another method. So we asked the people at Locarno to actually count with and without the weighting for a few years, and we compared the data. And we obtained something like that. So it showed that, in fact, it's proportional to the activity. So if you're really low in activity, you have mostly spots without penumbra, so the weighting, well, small spots, so the weighting is small, and then you go up in activity, and the weighting reaches a threshold around 17%. So it's very consistent. So what we find with one analysis is very close to what we find with another. So there were a lot of different estimations from Lockwood et al. In the beginning, the first article from Lockwood said that the jump was 11%. The discrepancy was between 11% for Lockwood and Leis-Valgaard, who said it was 20%. And as they are notoriously opposed to each other most of the time, it created a big problem. And so we jumped in the middle, and actually, with different studies, finished by agreeing on a value of 16 plus or minus 2%. So we are not at the 11% anymore. So the main output of this correction is this fact that the grand maximum, as we call it, for the modern era, doesn't seem to be in the data anymore. And so if you look again at this interesting reconstruction of solar activity over 2,000 years, what Mueller said in his article is that, in fact, the Greenland data seems to have more indirect effects that are not completely taken into account, and that the carbon-14 and the Antarctica beryllium-10 seem to be saying the right thing. So we are in agreement with, in fact, what the cosmogenic isotope says with the correction of the sunspot number. Now, let's go to the present. Now we have a network. So those numbers, we have 92 stations in 50 countries. Those numbers are from this week, I think. And so what is interesting is that this network is composed mostly of amateurs. So you could say that it's not good to have amateurs, but in fact, an amateur is a guy that could be observing from the backyard for 30 years in a row with the same telescope, the same eyes, mostly. And so it's really stable. While the professionals, they look like professionals. So UCL, of course, we are perfect and we do things perfectly, right? And so, but professionals, usually observatories, have a lot of turnover between different observers. So of course, it's not as good for stability as a guy observing for 30 years with the same telescope from his backyard. So we have two types of observers, of amateur observers, but it's in fact a good thing for the network. And for the future now, SILSO is undergoing a lot of improvements. So we introduced a versioning system of the sunspot number. So as I said, there is version 2.0 that is published, for which we have 3 of the 5 corrections I showed you. And there will be all other versions. So we will not always change the first number, and version 3.0 is not for next year. But we might change the 0.0 into point something when we manage to mostly agree on corrections and on how much we have to apply. You see, for this WALDMEIER jump, we all agreed that there was something, but we didn't agree on the date first. So at the beginning, we thought it was 1945, then 1946. It's not so easy to do because it wasn't documented. And then we had to agree on the size of the jump. So for this one, it's mostly settled, but it took a few years. And so this is a work in progress. And I actually now have a PhD student that will help us with the quality control of the whole network, so in real time or almost real time. This will be computed in the next 4 years. And put into action, implemented in the routines. Now let's go to the more details on this solar activity indice. So this well-known 11-year cycle is in fact not exactly 11 years. Everybody thinks it's 11 years. Well, we say 11 years and everything, but it's on average 11 years. But I think it varies between 9 and 14 years. But we'll see on the next slide that it's not exactly that. And there is a long-term variability in the length of the solar cycle, in the amplitude of the solar cycle, in the rise time and decline time. And here you have a graph from, I don't remember which article, but so if you compute the cycle lengths from minima to minima or from maxima to maxima, you have crosses if you go from minima and blue dots if you go from maxima. You have different lengths for these different cycles. And you can see on the graph that it goes approximately from 8 to 15. They are never the same. There is a cycle that comes back almost every time, but it's never the same. So if we look at the shape of a solar cycle, there is an asymmetry in the rise and decline that we call the WALDMEIER effect. You can see it on these 6 cycles. You can see it on the whole cycles back 400 years. There are double peaks, not all the time, but you can see it on. So here you have at the end it's cycle 24, 23, 22. So you can clearly see it on cycle 22 to 24. This double peak. You have to note that there are minima and maxima. So minima is between cycles, and maxima is one of those double peaks. Usually one is higher than the other, but it's not a sinusoid shape, as you can see. And the thing is that those minima are not real separations between cycles, because actually one cycle overlaps with the other. And there is a north-south asymmetry. Let's take a look at the WALDMEIER effect. Here you have a very nice slide that shows that when a cycle rises to a high number, it will rise really fast and decline really slowly. But if it's a small number, the maxima, it's almost symmetrical. It's not really symmetrical, but it seems to be symmetrical. And on the right, you have a graph that says the same thing. It shows for real cycles, you have the numbers. So if a cycle is really, really small in amplitude, like 50, the maximum, it will rise it will take a very long time to rise. But if it's really high, it will rise much faster. Sorry. Those double peaks now, you can see them on this graph. Those double peaks are what we call the GNEVYSHEV. I never know how to pronounce that thing. The GNEVYSHEV gap, from an article by the guy from that name in 1963. There is no real consensus on the origin of that double peak. It could be due to the north-south phase shift activity. So sometimes the north peaks before the south and vice versa. But there are some articles that actually say that there are double peaks in north and south themselves, so it's not so clear. Now there is a north-south asymmetry, there is a north-south coupling, so you can see here when the north dominates and when the south dominates in this graph. So north dominates when it's green and south when it's red. And the two hemispheres never get out of phase by more than approximately 2 years. There are some articles that say 10 months and some that say 1.8 years. So it's not a complete agreement here either. And now for the shape of a cycle, so you've seen this butterfly diagram in Frédéric's talks. But what's really interesting is that when one cycle ends, I should have a pointer. Do I? Oh yes. So let's look here, for example. Here you can see that there are spots from this cycle in 1943 or something, but there are also spots from the next cycle. So in fact, when you look at the sunspot number, you don't have the whole information. And when you look everywhere, you have definitions of minima and maxima that will actually take the date of the minima with the 13-month smooth sunspot number. But it doesn't give the whole information. If you want to compute the dynamo and things like that, those minima that are published are not the best way to do it. It's actually better to have the date of the last spot that appeared close to the equator for the and for the next cycle it would be the first spot that appeared at higher latitude. And so it's what's published at this moment, what you can see on all of the websites, NOAA website, even on our website, what we use for the data, for the computations of predictions and everything is usually minima. And those minima are computed from the 13-month smooth sunspot number, but it doesn't give the whole information. And I think there is an example in a living review by Attaway. I don't remember which cycles, but for example, there is a there is a minima for which the value is like 0 for 10 months, and so it's impossible to give the actual date of the minima. So it's not very accurate. So what would be nice is actually to have all of the positions, but we have them only with the Greenwich catalog and a few other catalogs. And if you have the positions, you could compute actually cycle by cycle with the latitude. So and this way you have the actual minima, you have the actual starting and ending date of a cycle. Those minima are not the actual starting and ending date of a cycle. Now, if you look at longer term periodicities, I put red and yellow squares on the, so there is the Gliese pair cycle that is well known, that we hear about here and there, that you can see here, in fact, but it's, we say 87 years, it's 87 plus or minus 50. It really depends on the studies you see and the Fourier analysis that was done on which sunspot number it was done, if it was smooth, not smooth, daily, and other. And there is the Suez cycle or De Vries cycle of 208 years. This time it's plus or minus 40 years, I think. So you can find studies where it's 187, studies where it's 200. There are many different studies. And there is the Oerstед cycle that you don't see here, of course, because this graph is only 400 years. That is found in the cosmogenic isotope data. But that one, of course, you cannot see on the 400 years of direct measurement, so it's I cannot even give you an error bar on that one. And there's also a very interesting GNEVYSHEV-OHL effect. So it's a two-cycle variations. It says that odd number cycles are higher than the preceding even number cycle. You can see it in that in those graphs here. There is a relation that can tell you something about the different cycles. And there are articles that say this rule doesn't exist, and articles that say it rules exist. This is a recent article by Tlatov. I can't remember the year, but I think it's a few years ago, at worst 2012 or something like that. And so it seems to be, in this article, it seems to be there. But there are articles where it's less clear. I think in the Living Review, the update of the Living Review by Attaway in 2015, there is a figure on that, but it's much less clear than the one on the right here, where you actually see a very nice variation. So, and now let's take a look at what we call the grand minima and the grand maxima. So this is an old figure, and I kept it on purpose because here you can see this very nice steep rise at the end that would say that there is a maximum, but in this new version of the group number, you don't have this. You have, though, a Dalton minimum here that is not written on this graph, I don't know why. There is the MAUNDER minimum here. And if you use cosmogenic data, you can find other grand minima or maxima that were given names. But the fact is that those cosmogenic data are really interesting because they give us insight farther than 400 years, but there are still problems with them, so this is subject to interpretation. And now for the MAUNDER minimum, this figure represents one of the latest reconstructions of this. In red, there is a very interesting article by Zolotova and Poniavin who used actually the maxima to reconstruct the MAUNDER minimum. So if you listen to them, it was just like every other period. You had solar cycle all the time. But well, if you listen to the expert, who is Vaquero, so Vaquero 2015, José Vaquero from Spain, and there were actually more cycles than what was found in the group sunspot number by Hoyt and Scatton in 1996, but they were not very high. But what's interesting is that now we know that it didn't completely stop from showing spots. There were spots, not many of them, but there were spots during the MAUNDER minimum. So what is this series, this long-term series used for? It's used for climate models, mostly. And I told you about the TSI because the TSI is what we use as input for the climate, for the sun part. It's used for the prediction of solar activity, for everything, I mean satellite and everyone sending cosmonauts in space, for example. And it's also used for space weather. Well, the base level of sunspot activity is used for space weather. So I get it for the end because it's really interesting. It's so an article by COP. I forgot to put the year. So I think it was in the topical issue of solar physics from last year. So by Greg Kopp, which studies the influence of the new sunspot number on the reconstructions of the SSI or TSI for different models. This is the satire. I didn't put the other one, but what you can actually see is that it's basically the same. After 1885, it changes quite a lot if you look before that. So for climate reconstructions in the past, it has a big influence. Now, can we use, oh, I miss a C. Can we use these data to predict the next cycles? Of course we can. We can use this data to predict the next cycle. There are different methods that could do that. On the SILSO website, we publish the McNish-Lincoln method that uses the distance to the average cycle to compute the next, I think it's 12 months ahead. I'm not absolutely sure, yeah. And so there are also methods that rely on the geomagnetic precursors, the AA index. It's based on a relation between the mean AA and the max of the cycle. And there are now a lot of predictions that are based on dynamo theory. The fact is that if you look at previous experience, like the predictions from solar cycle 24, for now, there are many different. And there were many predictions. You can see all of them here with error bars. Some of them don't have error bars. And the fact is that the actual value was here. There are so many inconsistencies between the predictions that as of now we still use old methods like the McNish-Lincoln method or the geomagnetic precursors because they're not so bad considering. But we are making a lot of progress in the dynamo theory predictions, but they are based on the models. So of course it's not so easy. But there are a few predictions for cycle 25 based on those dynamo theory models. But they range from it will be lower than cycle 24 to it will be higher than cycle 24 or even cycle 23. Well, so for now it's not really reliable. So I think that's it. And this is the list of references that were used throughout this seminar. There are other, of course, but I cannot put all of that on one slide. Thank you for listening.